Thank you, Ali. Good morning. It's so nice to see all of you here in person, especially in this very room about a year ago where I got my first COVID-19 vaccine shot. Good memories. So today, we have two exciting announcements representing actually some of the largest changes to Spark's project since the project's inception. But before I dive into those, I want to share with you some community updates. The world has changed forever in the last 2 years. In the middle of the pandemic, if you're like me, you picked up cooking, baking, and playing with big data. And that's why it's no surprise that Apache Spark's growth has been continuing going up, and it's now being downloaded more than 45 million times a month, just on Maven and PyPy alone. That's 45 million times a month. This is actually the 13th year of the Apache Spark's project history, and it's really astonishing how much the project's continuous success is getting. So in 2020, about 2 years ago, the HackerRank developer survey actually indicated for people with Apache Spark skills, your wages have gone up almost by 30% between 2019 and 2020. And this survey was echoed by another survey from Stack Overflow just last week, the 2022 Stack Overflow developer survey, that Spark was the top paying technology at the top. So congratulations to all of you, especially the ones that received the certificate earlier today. The survey really indicates the demand in the labor market for Spark skills. And now you know what to talk to your manager about in your next one-on-one. Right? And I also know it's kind of annoying to see Ruby on Rails just right up there above Spark. But it's not just stats that's growing. At ACM Sigma conference, also just happened 2 weeks ago in Philadelphia, Spark was awarded the ACM Sigma Systems Award. Now, this is a very big deal because Sigma is the most prestigious database community. It is actually where relational databases were born. The ACM Sigma System Award recognizes systems with significant impact on the theory and practice of large-scale data systems. And this is really a testament to Spark's adoption as well as its influence on the generation of systems to come. But Spark's not just resting on its past glories. There's so many changes that's happening across the board, going from Python to SQL to performance. Usually, a decade into the project, you kind of see the project start stagnating and not really changing that much. But there's so much change happening right now. I won't have time to go into any of the details. There's some examples on the screen here. I encourage you to check out the deep dive talk tomorrow at 2 p.m. to learn more about them. So for all of you that's here, you know that Spark's often associated with big compute, large clusters, thousands of machines, big applications, right? But the reality is data applications don't just live in data centers anymore. They can be everywhere. They can be interactive environments that cover notebooks, IDEs. They can happen in web applications. They can happen even in edge devices. Raspberry Pis, HomePods, your iPhones probably have a lot of applications that can benefit from the power of data. But the reality is you don't see Spark ubiquitous in all these environments. Why is that the case? So if you zoom in, you realize Spark has a monolithic driver. This monolithic driver runs both the user's applications as well as all of the Spark code. And this includes the analyzer, the optimizer, and the full-fledged distributed execution engine. This coupling of the monoliths of the user's application and the Spark code actually makes it very difficult to embed Spark in any of the sort of more remote environments. As a matter of fact, the opposite is happening. You have to embed the applications in Spark. So for people to work, some people work around this by figuring out, hey, why don't I just send SQL strings, for example, over from my application to sort of some sort of gateway that happens in Spark. But SQL doesn't actually capture the full expressiveness of Spark. It is just a much more limited subset. It's great, but it doesn't run, for example, your machine learning applications. Some other projects come up with their custom protocol to send code over, like Jupyter Notebooks with Jupyter Notebook kernels. But that's very, very difficult to debug. And for a lot of programming languages that simply don't have JVM interops, you can barely even get it working. Now, let's say you actually figure it all out and actually got some custom protocol going and it's really working. You run into a whole suite of multi-tenancy operational issues. And the fundamental issue here is the lack of isolation. All right? One application that's consuming too much memory and malbehaving might create a out of memory exception. But it doesn't just the application itself. It every other application in the same driver. A lot of other problems with dependency conflicts. It's also very, very difficult to upgrade your application or upgrade Spark because you have to upgrade all the application and Spark at the same time. Right? Same thing with debuggability because you might not actually have network connectivity onto the Spark clusters for security reasons. And observability as well. So with that, I'm super excited today to announce Spark Connect, which in my mind is the largest change to the project since the project's inception. Spark Connect enables applications anywhere to leverage the power of Spark, the full power of Spark. So what is Spark Connect? The idea is very simple. We want to create a decoupled architecture and a stable client-server protocol so we can embed a thin client in any applications. And this client API is designed to be thin, so you can really embed anywhere you want, even computation devices, devices with very, very little computation power. And it's designed in a way to be language agnostic, so you can actually use it in any programming language you want. Let's take a look at how this works. So we're creating, again, just a protocol between the client and the server. And this protocol is language agnostic, it's quite simple, and it's very stable. And the prototype actually uses gRPC and uses protobuf. All the client needs to do is you have your client's data frame API in any language you want, if the native language. And then it generates unresolved logical query plans based on proto, and sends the unresolved query plan over to the server, which is the Spark code, using gRPC. All of this happening in a language agnostic way. And the server can execute that query plan using the standard query optimization execution pipeline, and then sends the result back. Now again, using gRPC and Arrow in a language agnostic way back to the client, and the client can interpret the result and do whatever it wants with it. This is very similar to think about SQL, sending SQL strings over, but using JDBC, using ODBC, or using any of the client drivers you might be using for database drivers. But there's so much more than just sending SQL because you have the full power of the data frame API in Spark. So with this protocol and with thin clients we can create, now we can actually embed Spark in all of these devices, including the ones with very limited computation power. And such devices can actually drive and orchestrate all of the programs and actually offload the heavy lifting execution over to the cloud in the backend. So this architectural change also mitigates a lot of operational issues we just talked about. For example, applications that use too much memory actually the driver itself. Not only its own client, it has no impact on any other applications. Dependency conflicts are now isolated to the client itself. And it's much easier to upgrade because you can either upgrade the application one at a time or upgrade the server. As a matter of fact, if we design it right, you could even upgrade the server without changing the application at all to gain the benefit of all the latest performance and security patches. It's very easy to debug because you just use whatever native programming language toolchain to attach to application. You can do all your step-by-step debugging. Same thing with observability. So rather than me talking more about it, I would like to invite Martin Grun, the project lead from Databricks responsible for this contribution, onto stage to show you a demo. Welcome, Martin.
Thanks, Reynold. Thank you. All right, so we talked a lot about how can we actually demo Spark Connect. And all I got was a SQL query and an iPad. So let's see what we can do. All right, so I open this app here. I have a pre-configured Spark shell, and I will now create a data frame based on a SQL query that I've previously copied in my clipboard. And typing on an iPad is hard, so please bear with me a little bit. OK. All right, so here we have the SQL query that I got. I don't really know what it's doing, so the next thing I'm going to do is actually printing the metadata of the projected columns to get an idea what's in there. All right, so what happens now is that Spark Connect goes to the Spark cluster, resolves the plan, and gives me back the projected columns. All right, so I've seen Spark version 3.3. I'll create a new data frame in a whole PySpark notion that I know and love, select the date column, df.date. Then I will select the version 3.3. And lastly, the total number of downloads. Oops, and all right, total. And to make it more interesting, I will then sort the result by date in a descending order and only show the last 10 or the top 10 results. All right, cool. So, but what happens behind the scenes? So every Spark Connect plan has a built-in logical unresolved plan that Reynold already talked about, and I'm going to show you how this looks like. So you can always look at the composition of your Spark query at any point in time, and as you can see here, there's a secret query, a projection, and a limit. All right, so now let's just collect the data, and then we get the result back as a pandas data frame. Since it's a pandas data frame, I can use pandas directly on my iPad again to create a new column that then calculates the number of total downloads from Spark version 3.3 over the total number of downloads to get the ratio. Okay, so divided by S of total. Okay, and now I will just print the result. Okay, so again, it goes back to the server. And what we see now is that over just 7 days of releasing Spark 3.3, it went from 0% of the downloads to about 35% of the total PyPy downloads. And what you see here is that I used an iPad, Python on an iPad, I used Spark, I used Python, I used pandas all in one to show how easy it becomes to build modern data application. And with that, I'm giving back to Reynold. Thanks.
Thank you, Martin. I think that was actually his own personal iPad. Thank you for donating that. So, in case you haven't realized and noticed, what Martin is doing was actually, he was orchestrating all of this computation on his iPad, which offloads most of the heavy lifting part of downloading, crunching through like actually billions of records onto the cloud. All right. So 7 years ago, when we first started Databricks, we thought it would be so out of the realm of possibilities to run Spark on mobile that I personally wrote this blog post for April Fool's Day called Re-architecting Spark for Mobile Platforms. It was before Spark 2.0 even came out. We're at Spark 3.3 now. Wall Street Journal actually fell for it and called us and tried to verify the authenticity of this. But we were wrong. We didn't know this would be possible, and with Spark Connect, this could become actually a reality. So Spark Connect was officially voted as a SPIP just a couple of weeks ago, or Spark Project Improvement Proposal. The community is now working hard to actually bring it forward, and very likely you'll see experimental support for it in the next few releases, starting with Python, but obviously eventually rolling out to all the other programming languages as well. So the second thing I want to talk to you about today is about streaming. We have seen an explosive growth of streaming applications also, just in the past few years. And right now, just on Databricks alone, we have more than 1,200 customers building streaming applications and running streaming applications every day. And this has led to over 150% year-over-year growth of streaming jobs. So today, I want to tell you more about what we're doing with Spark Structured Streaming. And with that, I would actually like to invite Karthik onto stage. And Karthik is a well-known figure in the streaming community. He's the co-creator of Pulsar, Storm, and among other things. He was also the former CEO of Streamlio, which is a streaming company that's responsible behind the project Pulsar. And he happened to be the most technical CEO I know, on the planet. So welcome, Karthik.
Thanks for the intro, Reynolds. I think most technical title CEO goes to Ali. He gives a lot of great feedback on the design documents, deeper feedbacks. So I started Databricks last year, and one of the things that I wanted to find out was why Spark streaming is popular. So we talked to a lot of customers and users and found out there are a lot of reasons they use Spark streaming. And here are the top 5. First is unification, because we have batch APIs and streaming APIs are the same. So if you're already using Spark streaming, all you have to do is just change the configuration a little bit, and you can turn it into a streaming job. So the second, robust fault tolerance and recovery. So Spock automatically checkpoints at every stage of the processing and stores the state, and then whenever a failure occurs, it recovers from the previous state. So whenever failure occurs, it automatically recovers from the previous state. The failure recovery also is very fast in the sense like only the failed tasks are recovered. So it is opposed to the streaming systems like Flink, which allows you to restart the entire pipeline. So the third one is performance. So the structured streaming provides very high throughput with the seconds of latency at a lower cost, using full advantage of the performance optimization of the Spock's SQL engine. One of the deployment we have done around 14 million events that corresponds to 1.2 trillion events per day for the most challenging workloads. And the fourth, flexible operations, ability to do arbitrary logic and operations on the output of a streaming query using for each batch operation. It allows you to do a lot of what you call upserts and output to multiple sinks, etc. Then finally, we have the stateful streaming, which is inbuilt into Spark streaming itself. So it supports a lot of inbuilt stateful aggregations and joins and other operators with watermarks for bounded states. In addition, you can do arbitrary stateful stream processing as well, where you can write your own stateful operators in Java and Scala. So as Spark streaming grow, a lot of new emerging applications, developers started using it to develop these new applications. Let us look at a few of them. So first, proactive maintenance in oil drilling, where you continuously monitor the data and so that the drill bits do not strike a hard surface. So you have to do proactively monitor this data. Second one is elevated dispatch. So where you continuously monitor the elevated data for emergency purposes and dispatch and alert the dispatchers for any situations. Third, tracing microservices. Stitch the request and response from microservices that serve a web request for tracing and troubleshooting purposes. These applications expose some of the shortcomings of structured streaming. So if we address these shortcomings, we can even see a much more skyrocketed growth. So what are we doing about it? So before that, I wanted to find out what are the requirements that we need to, these emerging applications are driving. First is consistent sub-second latency. Second one is ease of expressing processing logic for complex use cases. Then the third, integration into very different cloud sources and sinks so that Spock's structured streaming can operate with multiple sources and sinks in the new era. So structured streaming needs to evolve to satisfy these new requirements. So what are we doing about it? So I'm very excited to announce Project Lightspeed that takes Spock's structured streaming to the next generation. So what is Project Lightspeed is all about? There are 4 pillars in Project Lightspeed. First, predictable low latency. We are targeting reduction in tail latency up to 2x. Second pillar is enhanced functionality, ability to capture advanced capability, introduce advanced capabilities to capture the processing logic very easily using new operators and APIs. Third, operations and troubleshooting, simplify deployment operations, troubleshooting, and so that you can get to the issues quickly and get the pipeline back up and running. And finally, kind of improve the connectors and ecosystem where you can connect to different systems in the cloud and write data into the sinks in the cloud, and also improve features like authentication and authorizations. So first, the next few slides, I will go through some of the highlights of Project Lightspeed. So the first one is about how we are going to achieve predictable low latency. So SSS, Spock structured streaming, has several bookkeepings. So one is at the start of the microbatch, another is at the end of the microbatch. So the start of the microbatch essentially plans what records constitute into the microbatch, and that is forced into external storage. Second, the microbatch is started and executed. And the third, the batch is marked as done. So that is the second bookkeeping at the end of the micro batch. So these bookkeepings has to be stored in storage before the start of the micro batch and end of the micro batch. So that is executed in sequence. So that causes a lot of latency. So when we did an implementation and measured it, we clocked around 440 milliseconds. So now, when the continuous streaming is occurring, in fact, like where micro batches are executed one after the other, so you don't need all these bookkeepings. You can simplify the bookkeeping further. So, so we can eliminate the mark batch done because the offset ranges itself serves as a marker. So now the offset ranges do not have to be forced into disk. Instead, it can be returned while the micro batch is executing or overlap with the micro batch execution. So this, when we did a POC implementation, it gave around 120 milliseconds. That is around close to 4x improvement or 73% improvement in latency in stateless pipelines. So second improvement in predictable low latency is improved state checkpointing. So currently, when the micro batch is executing, after the execution of the micro batch, the state is propagated to the external storage synchronous fashion before the next micro batch is started. So in the asynchronous checkpointing that we have implemented, so we overlap the micro batch execution with the propagation of the state asynchronously. This achieved another 20 to 30% in stateful pipelines, which is another major improvement. So in the next slide, let's look at some of the advanced functionality that we are doing, where we are going to use for Python as a first-class citizen. Spock's structured streaming pipelines can be programmed using multiple languages. One is Java, Scala, and Python, and SQL. Python is a popular choice by a lot of developers, and Python provides several APIs for DDL operations and DML operations like filtering, joins, aggregation, grouping, and windowing. But there is a gap, which is what we are going to address, and that's for arbitrary stateful processing. So there are two APIs that map group with state and flat map group with state, which allows the user to write their own stateful operators like exponential weighted average for the financial community and other operations. The challenge with this API is this is arbitrary Python code that needs to be executed in a JVM system, or it can be executed in an out-of-process system and bring the data back in. So there are challenges in implementing this as well. So the next, let's talk about how to improve debuggability. So this Spock streaming pipelines are very brittle even in any streaming systems. So there can be several reasons. One is surge in data, and resources are not adequately provisioned, and bug in users' code. So whole idea is to pinpoint the problem quickly and get the pipeline back up, especially most of the streaming pipelines are real time. So Spock's structured streaming provides a lot of metrics and logs and at every micro batch level. But what it doesn't provide is a timeline view of metrics for the operators. And the operators could be at different levels. One is the operator that is expressed at logical level and how it's optimized at the physical level, et cetera, right? So we need to provide a timeline view of the metrics for operators at the physical level. Then the group operators by executors and incorporate source and sink metrics so you have one single pane of glass. So, and to look at how the source is pumping the metrics and how Spock is processing the metrics, processing the records, then followed by how sinks are getting the data. So finally, connectors and ecosystem. So we are going to add more connectors for Amazon DynamoDB and Google Cloud PubSub, and also Sync for Amazon Kinesis to send some alerts and everything for operational pipelines. And we are going to improve existing connectors. First of all, performance improvement for Delta-like connectors so that we can write data faster into Delta. Second one is like incorporate the AWS IAM authentication for managed Kafka services from AWS. Then we are going to add a EFO enhancement for Amazon Kinesis, which allows you to do higher bandwidth. So, and many more features. In case if you're interested more in Lightspeed, a blog will go out live at 9:30. Please look it up, and we have a list of all the features that we are going to roll out in Lightspeed. And if you are interested in a community collaboration with us, there are a lot of Jiras that we have opened on the open source, and we are very welcome to work with the community. And if you are interested, come and talk to us, or come and talk to me. And that's all I had. Thank you.